Let's discuss a question from conduction basically. So you have two thermal circuits given, T1, T2 is the temperatures across, and you have two configurations in which the rods are arranged. Okay, and they are of identical dimensions, so the lengths and the areas are same, area of cross sections are same. So we asked to find out compare the ratio of heat transfer between A and B. So how do you write let's say in the first circuit or in the second circuit, QA is always the temperature difference across by the resistance provided by the thermal circuit. So this is resistance in the series. Okay, so this is T1 minus T2 by resistance in the series, and whereas in the other part QB, the rods are arranged in parallel, so it's delta T, or resistance in the parallel. So I'll write T1 minus T2, rods are arranged in parallel. So when you come to this thermal circuits, in the first configuration the rods are arranged line by line, so they form a series circuits, and the total resistance is sum of the resistance. So individual resistance are given by L by Ka, L by Ka for the first rod. And so the actual formula, I mean, for any, you have a rod here with the length L and area of cross section A, so with thermal conductivity K, the thermal resistance is given by L by Ka. So L is the length of the rod, Ka is the area of cross section, K is the thermal conductivity. So higher the thermal conductivity, entire heat will get transferred, resistance is less. That's the basic meaning. So for the first rod it's L by Ka, for the second it's L by, the conductivity is 2K, so into A. So this effectively becomes L by Ka 1 plus half, so that is 3 by 2K, 3 by 2Ka, or 3L by 2Ka. Now coming to resistance in the parallel, the resistance always behave, I mean, it's basically, you can write, they vary in the 1 by R effective will be 1 by R1 plus 1 by R2. That's how they vary, and this can be proved. I mean, you have a lot of ways to prove it. So you have to just the thermal, you have to take the heat transfer from each of the rod and add it, because in parallel the heat transfer gets added up, and then you can the effective heat transfer you can just write in terms of resistance in parallel, and you will get this formula. So it's easy to derive this. So now we need to substitute this L by Ka into L by 2Ka by, effectively we got this as L by 2Ka. So this will become L by Ka will gets cancel out in the numerator, so it will be 2 by 3. That's what we get, 2 by 3 here. I think there's no R1, sorry about this, there's no, when you take the mean of this and find out, there will not be any 2 here, so this 2 and this 2 gets cancelled, there will not be any 2 here, and there will be 1 by 3, so it's L by 3Ka. So this is L by 3Ka and this is 3L by 2K. Okay, that is the resistance in parallel. Okay, so if you compare this by this ratio, that's we are asked to find. So QA by QB basically becomes R parallel by R series. So R parallel is L by 3Ka, which we already got, and R series we got this, so 3L by 2Ka. So it is basically all the other dimensions will cancel, it basically 2 by 9. So this is just the question, how do you apply the heat transfer conduction Fourier law. So only thing is, idea is in series the resistance gets added up, in parallel they vary by this formula, and these are easy derivations, you can easily derive it. So answer is D. Thank you.